Hello, everybody, and welcome to today's presentation, MemSQL, the modern database for time series, real-time, and beyond, brought to you by MemSQL. Now, I would like to introduce you to our presenter, Eric Hansen. Eric is a principal product manager at MemSQL, responsible for query processing, extensibility, and geospatial feature areas. He is a PhD graduate of UC Berkeley, was an Air Force officer, a professor of computer science at the University of Florida, and a principal program manager and developer for SQL Server at Microsoft. Eric was a Hive committer for contributions to Stinger and is a technology expert on data warehousing, column stores, and vectorized query execution.
All right, thank you. Today, I'm pleased to be able to talk to you about MemSQL. It's a modern database platform that can be used for all different kinds of applications and has some excellent characteristics for use as a time series database. So before I get deep on how to process time series with MemSQL, I'm going to spend some time giving you an overview of MemSQL so you can understand, what kind of applications you can build using MemSQL and how the technology works. And once I've provided that background, I'll talk more about time series. So MemSQL is a scalable relational database system that supports both transactions and analytics. And at minimum, it's about 10 times faster and 3 times more cost effective than legacy database providers for similar applications and scale. MemSQL is, we refer to it as the no limits database because there's really no limit to the scale of data that you can process with MemSQL, because it uses scale out, which I'll talk more about. And you can do transactional workloads and analytical workloads on the same platform. So MemSQL provides really high performance for demanding applications, including very fast ingest and low latency queries. We can process queries in extremely fast and consistent interactive response time. And what's great about MemSQL is it's very familiar. It uses standard SQL, but because of its scalability, you can process data essentially with no limits on the scale or the throughput that you want to provide. We use a distributed architecture, and it uses standard ANSI SQL that you're used to from using other database management products. And for every workload and infrastructure, you can use MemSQL. So we have many customers using MemSQL on premises installed on their own equipment, and also a large number that are using MemSQL in the cloud. And it runs on all the major cloud platforms through an infrastructure as a service installation. So MemSQL has a unified architecture for processing both, for handling both transactional workloads, applications, as well as analytical workloads, for things like data warehouses and data marts and operational data stores. So one of the things that's really great for developers when they start to use MemSQL for scalable apps is that they really appreciate the very high speed ability to ingest data. And I'll talk in more detail about that later. We support fast bulk loading, as well as streaming data with what we call our pipelines feature, which I'll say a few more words about later. And we also have memory optimized tables. These are in-memory row store oriented tables for extremely low latency transactions, as well as analytics on smaller quantities of data. And we support disk optimized tables, which are column stores that can support tremendous scale, petabyte scale analytics and compression with compression and performance. Now, one of the nice things about MemSQL is that, it's as a general purpose SQL database, it has a very broad ecosystem of tools that work well with it. So on the left are data sources that work with MemSQL. For example, you can stream data in real time into MemSQL using Kafka, streaming into pipelines in MemSQL. It's a very convenient way to load data into MemSQL. Just dump data into a Kafka queue, and MemSQL will subscribe to that queue and be able to load data in real time into tables without writing any code to do that. Also, we support transformations with various tools like Spark and Informatica. We can ingest. We're partnering with a company that we work together with to build connectors to relational data stores. We support loading and connectivity with data lakes, including Hadoop, HDFS, and Amazon S3. And on the far right, you see that once you've got the data into MemSQL, you want to query it and report on it. So lots of application software already can connect to MemSQL because we use standard relational database connectivity capabilities like ODBC, and pretty much anything that connect to a MySQL system can connect to MemSQL. So there's a tremendous ecosystem of application software that can use MemSQL. You can write custom apps to connect to MemSQL easily with APIs that you're already accustomed to. And in addition, a broad range of BI tools and dashboarding systems can connect to MemSQL like Tableau, Looker, and MicroStrategy. You can run on bare metal, you can run on virtual machines, you can run on containers, you can run on-prem, in the cloud, or as a service. So as I mentioned before, MemSQL is highly scalable. It has a scale-out shared nothing architecture. And so here's an illustration of that with at the scalability level of what we call 4 leaf machines and 2 aggregators. So MemSQL has machines take 2 different roles. One is the aggregator, and clients connect to an aggregator and submit queries, run queries, and get results back. The data in MemSQL is partitioned across multiple leaf nodes. So each leaf node contains 1 or more data partitions. Typical scenarios, you have, say, 1 partition per core on your leaf nodes, and data is, queries can be processed in parallel with threads accessing each partition concurrently for high performance scan and high performance update. So there's typically a master, the way MemSQL is configured at any one time, there's always 1 master aggregator, and then there can be multiple child aggregators, which are a client can connect to any of those aggregators and run queries. The master aggregator is the owner and manager of the cluster that orchestrates the other nodes in the system. And you can do things like, on the fly, you can add leaves, you can add aggregators. So if you need to expand your cluster, you can bring in a new server or 2 or however many you need, install MemSQL software on those servers, join them to your cluster, and then rebalance the partitions of data across the leaf servers that you have to even out the workload, and that can be done online. So you can grow your clusters online. So in addition to this scalable architecture, MemSQL, as I said, can be used for transactional applications and analytical applications like data warehouses and data marts. And so the technology we provide to support these different applications and different application roles is that we have two different storage structures. We've got an in-memory row store and a memory optimized column store. So it's a disk-based column store where the data takes is highly compressed, and you can store the data on disk. So there's no limit to how much data you can store based on how much RAM you have in your cluster. So our in-memory row store is very good for transactional applications. You can stream raw data in. You can aggregate at ingest time if you want to, using on duplicate key update, which is a form of upsert that's supported in our SQL syntax. And you can, that means you can either insert a row if there's no key for that already stored for that row, or if that key is already present, you can update an existing row. And so you can do streaming aggregation to create summary aggregates if you want to, using that approach. We also, using our in-memory row store, we can support thousands of concurrent queries, aggregating thousands of rows with sub-second response time. That means all of them concurrently are getting sub-second response time. You can get very consistent and low variance response time with our in-memory row store. That's one of the things, when I asked some of our customers who are in the financial industry, what they really like about the MemSQL row store, they told me that they love the low variance in response time, so that they can get queries to run in milliseconds every single time, because it's in memory all the time, that you don't have to worry about cold start, like when you reboot your server, you're getting initially some slow response time as you drag data back into memory, for example. It's when the system's up and queryable, you get the same response time almost every time, or virtually every time, with very low variance. For pure analytical workloads, the Columnstore is appropriate for those, and you can stream raw data in and store it with essentially limitless capacity, and you can aggregate at query time for maximum flexibility. So you don't really have to pre-aggregate or pre-summarize your data to get amazing response time with the Columnstore. And with Columnstore, query execution technology is a little different. I'll talk more about that later, but we can support hundreds of concurrent queries against Columnstore, each of which are aggregating millions of rows on the fly with sub-second response times. And if you have lower concurrency, you can process billions of rows in a fraction of a second for a single query. And some of you may have seen, we did a demonstration last year processing data at over 1 trillion rows per second while processing a single query. So if you haven't seen that, Google for trillion rows per second on MemSQL, and you'll see a neat blog post and demo about that. To go a little bit deeper on our row and column orientations for storing data, the row store format in MemSQL has all the data pinned in memory. So the data is stored in memory in what we call a skip list data structure. It's a pointer linked ordered data structure that's extremely fast, that can look up rows in a fraction of a millisecond. And it's all in memory for that consistent response time that people really love. With the row store, we can scan data at about 40 million rows per second per core to do a scan or a query, which may also include an aggregate. And that is really tremendous performance. And the way we get that is by compiling queries to machine code, and because we're using a lightweight in-memory data structure, which is much lighter weight to process than a traditional row-oriented data structure that you might have used in other database products like SQL Server, Oracle, Postgres, MySQL. The row-oriented structures in those systems are, most of them can process data around 1 to 2 million rows per second per core. So using our in-memory and compilation advantages, we're more than an order of magnitude faster than that for in-memory row store. And that's where that cost advantage comes compared to competing products that I mentioned earlier on in the talk. And with row store, you can do streaming or batch insert. You can use a bulk loader. You can use our MemSQL pipelines capability to do streaming load from Kafka or from a file system. And we can select and update individual rows very efficiently and have row level locking for update operations. In our column orientation, we can store, typically we store data on solid state disks, and we can scan and process greater than 200 million rows per second per core using compilation and vectorization. And again, you can do streaming or batch insert. You get compression ratios that can be 5 to 10 times, and locking is at a little coarser granularity. It's at the granularity of what we call a segment, which is like a 1,000,000 row chunk of a table. And we use columnar compression techniques like dictionary encoding and run length encoding to get that tremendous compression and also some query execution speedups. So one thing that's important to know about MemSQL is even though MemSQL has an in-memory row store storage structure for transactional application support, the data is persistent. It's permanent. So when you commit a transaction, the data is permanent. Even if you restart your cluster, it's still going to be there. If it crashes and restarts, or you manually restart it for any reason, the data will be there. So the way our persistence works for in-memory row stores is through two mechanisms. One is a snapshot. So periodically we take a snapshot of in-memory tables and write that out to disk on a partition-wise basis. And then for each partition of data, there's a log file, a write-ahead log file that we of course append to when we're doing updates to the data. So when if you want persistence and transactionality, this is these things provide that. So you don't have to worry about losing data. So it's a common misconception about MemSQL is that it's an in-memory only cache because our name is MemSQL. So, but people that understand the technology a little more understand that we provide full transactionality and persistence, and the in-memory is used as a performance accelerator. So querying the column store in MemSQL is really, really fast. So the columnar orientation is designed for fast data aggregation. And we have special code in our system that uses single instruction multiple data, or SIMD instructions, which are a low-level parallelism mechanism that's available in Intel chip. So you can do like 4 or 8 or 16 operations in a single clock cycle, a single instruction. And so we use that low-level parallelism on our column store, and we also perform operations directly on compressed data, and in addition use what's called vectorization, where instead of processing one row at a time, we process a block of like 4,000 rows at a time, and each column within that block of 4,000 rows is stored in an array or a vector, so that you can access it and process all the elements in that vector very, very efficiently using very tight loops of code and using SIMD instructions. And so we also, in our column stores, they have a sort key, and I mentioned the concept of a segment where each table is broken into 1,000,000 row chunks called segments. The data is sorted by your sort key if you want to. You can specify no key if you don't feel you need one, but typically you'll specify a sort key, like on a time column is often used. And then we can do what's called segment elimination to reduce the need for full scans. So if you have a filter in your query, like, that's on, only the data that's less than 1 week old, for example, we don't have to look at the whole table. We can use there's metadata on each column that has the minimum and maximum value for each segment. And we can skip entire segments if we know that nothing in those segments qualifies based on a filter predicate in your query. And we can even do segment elimination through join. It's common with data warehousing to use a date dimension table and have your date filters implied through when you join the date dimension to a fact table, you will get you can eliminate data that way from the fact table, and we can do segment elimination during our fact table scans, even when you imply the date filter through a join with the date dimension. All right, so that's the basics of MemSQL. Again, it's a super high performance system that can support transactions with our in-memory row store, can support analytics with our disk-based Columnstore, and we scale out for limitless performance and limitless scale. And so now let me turn to time series. So MemSQL is a fantastic time series database, and the way we support time series is through these mechanisms. SQL first and foremost. So SQL supports a lot of powerful capability for filtering, joining, aggregating, and that you need that kind of capability when processing time series data. It's not, that's a general purpose capability, and it's needed and applicable for time series as well. We support transactions. So if you're doing time series, like any application, you want your data to be permanent and secure and consistent. So transaction support in MemSQL makes that possible. One of the things that really people love about processing time series data with MemSQL is fast and easy ingest. I talked about the ability to ingest data in multiple ways, including inserting the data just with regular insert statements, a bulk loader, load data, as well as MemSQL pipelines. So whatever technique is most convenient for you, you can use that technique, and the performance is very fast. So we also support fast query processing with vectorization and compilation. We compile queries to machine code. So I talked earlier about how MemSQL is typically at least an order of magnitude faster than legacy row store oriented databases. The one key reason for that is that we compile our queries to machine code as when they access our row store, they're executing code directly rather than being interpreted as those legacy databases do. We also support window functions, and I'll get into that in detail later on. And we support extensibility with, especially it's relevant here for time series is stored procedure support, user-defined functions, and user-defined aggregate functions. All three of these are useful for managing time series. And we have excellent data compression. So, time series events can be very numerous, voluminous, and so it's important to be able to compress data in some cases to save storage. And our columnar data compression does an excellent job of compressing time series events. So MemSQL is used today in some key industries where there's intensive use of time series data. And so we have customers in these different industries: energy and utilities, financial services, media and telecommunications, and high technology. These are not all the industries that are using MemSQL, but these four in particular, we have a lot of customers in these industries, and these industries use time series data. So I've alluded to this already, but the place that MemSQL really shines and does a fantastic job for time series is in those time series use cases where there are these requirements. There's a requirement for a high ingest rate. That is, you've got a lot of events per second coming in, or you need to load data extremely fast, say periodically. So high ingest rate. And then number 2 is you need low latency queries, very fast interactive response time for queries. And at the same time, you've got a high rate of concurrent queries. So if you've got these 3 requirements, then MemSQL is a really good choice for time series data. And it's not essential that you have all these 3 requirements, but if you've got these 3 requirements, then MemSQL is really an outstanding candidate for managing your time series data. So for ingesting data into MemSQL, whether your application is a time series application or some other type of application, again, we can load data very fast. So you can load data with just insert statements or upsert, like I showed before, or load data. Also, we support streaming load with a facility called pipelines. So you can create a pipeline that references a Kafka queue or a file folder in your Linux file system, or S3 or Azure Blob Store. Then you start the pipeline, and we directly load the messages from a Kafka queue or files that land in the file folder that you pointed us at. And so you don't need a fetch execute loop in your application. We handle that for you with our pipelines approach. So it's a really convenient way to load data that's streaming into your system. And you can also transform the data with pipelines using external scripts written in Python or any language you want using a standard interface. So it's convenient to load with pipelines, and you can transform the data if you need to. We support transactional consistency in our loader. So if you load a file, it's either all going to load or none of it's going to load, and queries will see all of it or none of it. We support exactly once semantics with Kafka pipelines. And we support native integrations for Kafka, AWS S3, Azure Blob Store, and HDFS. So just a little data point about what we can do with data ingestion. You can ingest data phenomenally fast. I can't emphasize this enough into MemSQL. So I did an experiment. I got an opportunity, but working with our partner at Intel, to use a Xeon Platinum server that had it was a single server that had 2 Xeon Platinum chips with 28 cores each, and high performance SSDs, solid state disks attached. And I configured it as a cluster. Some people call it a cluster in a box, but it had 2 leaves and 1 aggregator, but they were all installed on this same machine. And then I just inserted data and updated data with a driver that was highly concurrent, that had lots and lots of concurrent connections that were running inserts and updates or upserts simultaneously, and was able to drive 2.85 million rows per second, insert and update on a single server. So, that is a phenomenal rate. I mean, very few applications have to drive much beyond that. But if you need to scale to ingest data faster than that, we can do it. You just have to add more nodes and scale out. So let's talk about how to query data effectively with time, when it's time series data. Again, we support full SQL. We support a SQL extension that's part of the, it's part of the SQL standard at this time, called window functions, which some of you may have used in the past. We have a full window function capability that I'll talk in more detail about. And we support extensibility. UDFs, user-defined aggregate functions, and stored procs. So window functions allow you to aggregate data over a window of rows. So the way they work is you have to specify you're partitioning your input set of rows by a partition key, and then within each partition you will have an ordering or sort order, and the window functions compute a result for each row within a partition, and so the window function result depends on the order of the rows within that partition. So an example is illustrated on the right there. You may have an input set of rows like that entire larger block, and you see the purple color between the start and end is your window. And there's a concept of the beginning of the window, the end of the window, and the current row within the window that you can specify with SQL using this new extension in SQL for window functions. So we support a bunch of different window functions, which I won't have time to get into in detail, but we support ranking functions as well as value functions like lag and lead, and aggregate functions, the basic aggregates like sum, min, max, average, count, etc. And then special percentile functions to show, to give you a percentile value. So I'm going to give a simple example of sort of a time series application just based on a tick stream. Imagine that you have very simple financial tick stream, which has a table called tick, which has a high resolution date time 6. So that's one thing I should discuss, is that we do support a date time or timestamp type, which has 6 digits after the decimal place. So it supports resolution down to the microsecond, which is a kind of high resolution timestamp you may need for some of your time series applications. And we support, okay, so this example table, I've got a high resolution timestamp and then a stock symbol and then the trade price. This is oversimplified, but I just want to use this simple example for some future queries I'm going to show you. So one important thing that you may need to do with time series data is to smooth the data. So you might have ticks coming in, or you might have events coming into a time series, and perhaps that there's a lot of noise in those events and the curve that looks jagged. You want to smooth it out for easier display, the easier understanding for your users. So you can do that with window functions in MemSQL. So this is an example of a query that computes the moving average over the last 4 entries in a time series. And in this case, the example is just pulling out the stock ABC, and we want to know, what the stock symbol is, what the timestamp is, the original price, and the smooth price. So you can see there in the tabular output below how price moves up and down a little bit chunky, and then the smooth price, averages over a sliding window of between 3 rows preceding and the current row. So that's how we get the 4 entries that we're averaging over for the smooth price. And you can define that window any way you want. It can be, the entire, it could be, you could average over the entire window, or, rows, preceding and the current row, or rows from preceding the current row to after the current row. So you can define the window however you like. Another important operation that people want to do on time series data is to aggregate over well-defined time buckets. This is called time bucketing. And you can convert, your goals when doing time bucketing maybe you want to convert an irregular time series to a regular time series. So an irregular time series has entries at irregular intervals. They may arrive at random intervals, and so you might not have, say, one entry every second. You might have, an arrival time on average, one entry every half a second, but it may be like a statistical process, like a Poisson process of arrival time. So you might have several seconds between arrivals of ticks. And you might want to convert that so you've got one entry every second. And so that's something you can do with time bucketing. Another application of time bucketing is if you may want to convert a high resolution time series to a lower resolution. For example, you might have one entry per second, and you might want to convert it to have one entry per minute. That's reducing the resolution of your time series. There are a couple of different ways you can do time bucketing in MemSQL. One is to group by a time expression. So for example, that query that says select TS : greater than date time and so on, that first one, that expression TS : greater date time, that's a typecast in MemSQL's SQL, and it converts that timestamp to a date time, not a date time 6. So that is going to have resolution of a single second. We won't have fractional seconds. And so you can convert to date time, take an aggregate, and then group by the first expression and order by the first expression to get that converts to that'll convert a high resolution time series to a second granularity time series. There's also you can also use user-defined functions to do time bucketing, and I've written a time bucket function which takes two arguments. The first argument is a time pattern that says like 1 second, 1 minute, 3 seconds, etc. So you can define with sort of a phrase what your time bucket width is, and the second argument is the timestamp. So you could do this with an expression in the query, but just as a simplification, I've written this time bucket user-defined function, and there's a blog post that'll be coming out today. Please see my blog that has the full text of this time series time bucket function. So in this example, it basically does something similar to the one above, but it's maybe a little easier to read because this time bucket function is kind of self-explanatory. So another important kind of application of time series is the ability to produce what's called a candlestick chart. So candlestick charts are a popular type of chart in the financial industry in particular. And basically they show you the high, low, open, and close for a specific period. So you've probably seen these in the financial papers, but this is an example, illustration of a candlestick chart, that picture below. And so you might ask, how do you compute a candlestick chart with MemSQL? So you can use SQL, standard SQL, to compute a candlestick chart in MemSQL. So here's an example query which generates a table that can be directly, converted to a candlestick chart by a reporting tool, and it uses 3-minute intervals. So suppose you have a bunch of raw data as ticks, and you want to produce a candlestick chart with one, with each 3-minute interval has a candlestick. You can do it like this. So this query uses window functions, and it uses common table expressions. So that with ranked as, and then there's a subquery there. That subquery is called a common table expression, and ranked is the name of that common table expression. And then the select at the bottom can reference the common table expression and perform additional processing on it. So the subquery produces uses several window functions, and it uses this thing called the window clause. You see window W as partition by symbol and time bucket 3 minutes, and then order by timestamp, rows between unbounded preceding and unbounded following. So what this says is each of these windowed aggregates up above, like rank, min, max, first value, and last value, is computed over the entire window. So that makes sure that we get the, since we're the entire window is the range that we're computing these aggregates over, we get the first value and last value correctly in that range. And then the ranking function is used. We want to pick out just one row for the entire window, for the entire partition. And so in order to do that, we basically filter on the rank. So pull out the first one. It's where r equals 1 pulls out the row that has it's the first one in the sorted series for a partition. And so we can run that query and get a result that has a candlestick chart. Another important thing that you may need to do with time series is interpolation. So you may have a time series that has gaps in it, like maybe you've got an entry for 1001, 1002, and 1004, but you're missing 1003. You may want to fill in the gap, and with interpolation may want to use maybe simple interpolation that just fills in the value with the previous value, or linear interpolation that computes like a linear slope between the two bounding values and fills in the missing entries. So you can do interpolation with MemSQL using a stored procedure, and we've got customers in production using stored procedures to do interpolation. And our stored procedures can output row sets using an echo statement you can actually send a row set back to the client with a stored procedure that way and do interpolation. Another capability that's useful for managing time series in MemSQL is the use of user-defined aggregate functions. So I already showed you how to do a candle chart and to use it had first and last aggregates that are standard built-in MemSQL windowed aggregates. But you might want to be able to simplify your query. You can create some special first and last aggregates with user-defined aggregate functions, and that's what I've done here in this example. So I've created a user-defined aggregate for called first, and I'm using it with that time bucket function that I mentioned. And you can you see how simple that query is, just 5 simple lines of SQL to find the the first value in a 3-minute interval against that ticks table for one stock symbol ABC in this case. So I don't have time to go over in detail how that user-defined function works, but I just wanted to show you a quick illustration of what that code looks like. So here's first, I'm not going to go over it line by line, but just to show you kind of the level of complexity and what our stored procedure and function language looks like. This is called MPSQL for MemSQL Procedural SQL. So we've got, here's a time bucket scalar function that has a bucket descriptor and a timestamp as arguments, and you can see the body of the function parses apart the time descriptor and then uses expressions to figure out to return to bucketize basically the timestamp into the correct granularity and returns that. And then here is an example of implementation of the first aggregate user-defined aggregate function. So our user-defined aggregate functions have initializers, iterators, a merge function to merge state from 2 different threads that are computing information for that aggregate, and then a terminate function to get the result of the aggregate. And you create the aggregate, you define its name and its argument types, what it returns, and then you have to tell it which user-defined scalar functions are used to implement each of those operations that are used to implement that user-defined aggregate, including the initialize, iterate, merge, and terminate. So I'm not going to go over that in fine detail, but that's just a little bit of an example of how how you can use user-defined aggregates to process time series data. And let's go back to this candlestick chart example. Let me see if I can pull that down. So I'm going to run this query, this candlestick query, just so you can see it in action. So, I ran that query, and you see in a fraction of a second, we got back a tabular output that can be rendered as a candlestick chart. All right, so just to summarize, MemSQL can solve time series development challenges for you in a number of different ways. Because we have incredibly high performance, through our scale out, our compilation, and our vectorization, your time series queries will run fast, and we can scale to handle large workloads and large data volumes. Also, we support very fast ingest of time series events through just regular insert statements, upserts, load, or pipelines. Also, we support the powerful SQL window function extensions that are terrific for time series. They're fully built into MemSQL and native implementations. And if you want, you can make your time series processing a little bit easier using user-defined functions and user-defined aggregate functions and stored procedures, just to add more power and flexibility to your time series processing. And finally, MemSQL provides all the capabilities of a distributed SQL DBMS. So, if you're going to build a time series application, you may have a choice between using a purpose-built time series database that's specific to time series, or a general purpose database like MemSQL. If you choose a general purpose database, you're going to have a lot of extra benefits that come with that, including SQL, transactions, backup and restore, full cluster management, row store, indexes on the row store, Columnstore, concurrency, high availability. You can handle general purpose applications that are transactional. You can handle analytical applications like data warehouses, data marts, operational data stores, or analytical extensions to your operational apps. You've got the full SQL provided to do outer joins and these kinds of things that may be difficult to do in a time series specific database. So the generality of MemSQL can handle a lot of different application needs. And moreover, it can still handle time series really effectively with powerful window functions and user-defined extensions. So please try MemSQL today if you haven't tried it already. You download our MemSQL from memsql.com/download. You can use our free edition. This can be used free in production for up to 128 gigs of RAM capacity, and use our enterprise trial, which has unlimited scale for up to 30 days for development. And please check out a new blog post, which should be coming out today at that URL. You can go to our blogs and see my new blog post, which has the full text of the time bucket function and those user-defined aggregates that I described today, first and last, for processing time series. And it also it's in document form, covers a lot of the material that I discussed today. All right, thank you. At this point, I'm ready to take questions.
Fantastic, thanks, Eric. And just to introduce myself, this is Mike Boyarski. I'm part of the MemSQL team. I'll be helping Eric out with some of these questions. So now's a great time to submit those. We've got already a good queue in the works, but you're welcome to add more as we go. So we'll start off, Eric, with I've got a couple questions around just comparing our technology to other time series offerings out there. And without getting into specific, specific names of technologies, maybe from a category perspective, there's a few technologies out there that build time series functions on top of Postgres. And so the general question is, what would make the MemSQL offering, different over something that is implemented on top of a Postgres based solution?
So MemSQL, because the main difference is the performance that you're going to get with MemSQL for ingest and for large scale query. So a Postgres oriented system, depending on what you're looking at, it may not provide scale out. So that will provide a scale limit. And also because MemSQL's got an in-memory row store and a disk-based column store, and we compile queries to machine code, we use vectorization for columnar queries. We have a higher performance query processing engine than you might get for standard query processing operations on Postgres.
Great. And then in terms of technologies that are implemented on top of more of a NoSQL style approach, which is, there's a bunch of different technologies out there. What would be some differences or advantages between, a NoSQL based time series implementation versus something that MemSQL offers?
So I think that so standard NoSQL systems don't necessarily have special time series support, and they often don't support full SQL. So one thing that you find different about MemSQL is that we do support full SQL and the window functions, which are good for processing time series style queries. So that's the main difference that I see.
Yep, great. Okay. All right. And so another question that was asked around the ingestion rate and how can that be increased? What are techniques that can allow MemSQL to extend the throughput from an ingest perspective?
Sure. So you saw earlier in the talk I showed ingesting like 2.85 million rows per second into a single server transactionally. So that's a pretty phenomenal rate. But as I said, if you need to scale more than that, because we support scale out, you can add more servers, and we can load data, at the basically limited only by the how much hardware you're providing. So you can add extra aggregators and extra leaves. If you're inserting data directly by adding aggregators, you can increase the insert rate that you can handle. And also our pipelines capability is fully parallel at the leaf level. So if you want to do ingest through pipelines, you can scale that out by adding more leaves to your cluster. So in addition, our loader is pretty high performance, and we've done some work recently, like in the last release, the 6.7 release, we introduced dynamic data compression into our loader, because when you're loading data, you may need to shuffle the data across your nodes as part of that operation. And we have an adaptive data compression strategy that compresses data as it's flowing between the leaves over our internal network, if needed, in order to get, if we're bandwidth limited on the network. So that, there's a bunch of techniques you can use to increase the performance of MemSQL for loading by scaling. And then just the implementation of our load is pretty high performance through techniques like compilation to machine code and also dynamic compression.
Okay, great. Thank you. Another question was around basically snapshotting. So the specific question was, how long does it take? And and that's always dependent on the amount of data. So maybe you could explain a little bit about how MemSQL supports snapshotting. In particular, the question had a detail around, can snapshots be made for a partition of the data?
So when you take a snapshot, you don't snapshot a specific partition, but the snapshots process, you can trigger it with a command if you want, but you typically never do that. You just start up the system and the snapshots happen in the background fully online, and you don't notice any pauses or anything like that. So it really, it really doesn't matter how long the snapshot takes for most people, but it snapshots on a very large in-memory row store might take a few minutes to run from beginning to end, but because it's fully online and you don't really notice any pauses or anything like that.
Yep. Okay. Is the storage orientation for the database need to be set up ahead of time, or how is the setup of the data stored between the row store and the column store?
That's a really good question. So you set it up when you create a table. So when you create a table, you can either create it by default, which gives you a row store, or you can specify some extra keywords in your create table statement to tell it to make it a column store. And so the storage is either a row store or a column store on a per table basis, and you define that when you create the table. Some customers are building applications that use a hybrid row store column store approach with views. So they create a union all view that has like the newer data in a row store and the older data in a column store table. And then we're able to, with our segment elimination and index seek capability, we're able to process queries against the views like that, very efficiently.
Yep. Okay. We're getting up close to the end of the time here. The questions are rolling in, so we'll just try to get a few more. So, are stored procedures compiled to machine code? And if yes, is that machine code only for Intel chip architectures?
The answer to that is yes, they are compiled to machine code, and yes, it's only for Intel architectures at this point. So we use the LLVM compiler framework to generate code, and we haven't had a demand for working on other hardware besides Intel, but technically it could be feasible, but right now it's just Intel.
Great. All right, and the last one is around limitations, if any, to pipelines, is in terms of the number of concurrent or parallel pipelines used. Is there any sort of physical limitations there?
I'm not aware of any limitations other than the capacity of your cluster, the hardware capacity of the cluster. I don't think there's any fixed limits.
Excellent. Okay, and there was a question around, will folks get the deck? And I believe there's a recording that will be shared after today. So yes, the answer is you'll get access to the content, and that concludes today's topic. So I want to thank you all